Hey everybody, look, we are in chapter 2. We are moving forward. We changed up a couple things, so you need to get your packet and let's get started with section 2.1 notes. Here's a couple things that we've done differently. So we've got the same setup where we're doing our vocabulary and our drawings. Here's one thing I want you to notice after the examples. You've got a couple of problems that you need to try on your own, so my expectation is that you're going to do it. So when you have notes and you're turning them in, you need to do the notes, which is copying what I'm talking about, and then I need to see this effort. Your notes are not complete if you do not try these problems, in addition to copying the stuff that I have. With that in mind, let's get started. So what we're going to be talking about in this section in chapter 2, section 1, is how to use inductive reasoning. As usual, go ahead, write the date, and we're going to get started with our vocabulary. Our first vocabulary word is inductive reasoning. So inductive reasoning is the idea of looking for a pattern and then trying to find a conclusion. So you're looking for a pattern and then you're trying to draw a conclusion from that pattern or that whatever information you're given. And so that's going to be what you are using. That's how you use inductive reasoning. And at the end, when you try to come up with the conclusion, that's called a conjecture, which is going to lead us to our next definition. But before we go there, let's talk about inductive reasoning just a little bit more. So let's say I'm in class and I'm saying things like, okay, guys, I want you to do a lot of problems. I want you to do problem 2, then 4, then 6, then 8, then 10. And you know I'm going to keep going. What would you guess is my next problem that I choose? Hopefully you said 12. And if you said 12, you would be making a conjecture that I'm either choosing even numbers or I'm skipping every other number. Both conjectures is just your idea that you have given the fact that you looked at a pattern of behavior. For me, calling on all these even numbers. Does that make sense? All right, so let's see if we can kind of define conjecture in a similar way. So your conjecture is really an unproven statement that is based on observation. So just like if I were calling out problems and I'm happen to be calling all the even problems out, 2, 4, 6, 8, 10, and you say, oh, she's calling out the next even number, definitely, because you're looking at that pattern. I could call out 13. It's not the next even number. Your conjecture could be wrong, but it also could be right. So it's unproven. A conjecture is unproven, but it is a statement that's based on observation and inductive reasoning. So our next word is counterexample, and a counterexample is a specific case when the conjecture is false. So basically we find something that would negate it, that would say, hey, that's not true. For example, okay, so here's an example. Let us create this conjecture. In geometry class, we will do IXL this Wednesday. That's a pretty decent conjecture. We've done IXL in the past on Wednesdays. It happens a lot of Wednesdays. In fact, probably most Wednesdays. So a student to say that would be making a conjecture. They don't know my lesson plan. They have no idea what my plan is, but they're looking at a past experience. They're using inductive reasoning to think through the fact that, yeah, Wednesdays we do IXL. Here's the counterexample. The counterexample is that this Wednesday, we're going to be doing map testing. So the fact that we're doing map testing this Wednesday, as opposed to the regular IXL, that would be a counterexample to the conjecture that we're doing IXL this week. Make sense? Okay. So we are on to the examples. So let's look at example 1. You have it printed in your packet. It says describe how to sketch the fourth figure in the pattern and then sketch the fourth figure in the pattern. So what we're going to do is use inductive reasoning. We're going to look at the first figure, then the next one, and we're going to observe the differences and the changes. So one thing I'm seeing here is that there's 2. Here there's 4. So we went from 2 to 4 and to 6. We went from 2 pieces or 2, cuts in the circle, or a circle cut into 2 pieces. The circle cut into 4 equal pieces, the circle cut into 6 equal pieces, what do you think the next one would be? My conjecture is that the next one would probably be 8 pieces. So I'm going to draw a circle and I'm going to cut it into 8 equivalent pieces by first cutting it in half in both directions and then cutting those fourths into halves again. And so now I've got to figure out, what are we shading? Here we shade 1 out of 2. Here we shade 1 out of 4. 1 out of 6, or 1/6. So it looks like it makes sense for us to shade 1 out of 8. And so that's what we're doing here. So what we've used is inductive reasoning. We looked at the pattern and we saw if we can continue it. And that's what we did. Let's look at this next one. Sometimes patterns aren't figures, they're numbers. And so what we need to do is see if there's a way to figure out what's going on. So we start off with -7. We move to -21. And this is where multiplication facts are important, my friends, for you to notice relationships and to see things. So it says describe the pattern and then write the next 3 numbers in the pattern. So we're looking for 1, 2, and 3. I think you should pause me and see if you can figure it out. All right. If you pause me and you weren't sure what was going on, or if you did and you want to check, let's talk about what I see. So I'm seeing -7 to 21. I'm immediately thinking about multiplying by 3. And then when I take 21 and I multiply it by 3 again, totally looks like 63 is going to happen. If I continue this process of multiplying by 3, I will get 189. So for me, it's going to be about multiplying by 3 because that's how I get from one number to the next. So to get these next couple of numbers, I'm going to multiply by 3. So I'll take 189, I'll multiply that by 3. So I get 567. And then when I multiply that by 3, let me go ahead and get this here. If I multiply that by 3, I get 1,701. And then when I multiply that by 3, I get 5,103 or 5,103. And so that's how I continue that pattern. However, my bad, they're all negative. So when I multiply a positive times a negative, I get a negative. So -7 times a +3 gives me that -21. And I constantly multiply by a +3, so I keep getting a negative answer. All right, let's go ahead and see if we could practice making a conjecture. So for this example, we got to draw some pictures, so give yourself a little bit of space. It says, given 5 collinear points, make a conjecture about the number of ways to connect different pairs of points. Let's think about what we have. So 5 collinear points would be 1, 2, 3, 4, and 5. And we need to make a conjecture about how to connect them. What we should start off with is 1, and then 2, and then 3, and see if we could figure out some kind of relationship. I'll show you what I mean. So start off with 1 point. How many ways can I connect 1 point to itself? Well, to another, really to a different point. There's no way for me to connect 1 point to a different point if that's the only thing I have. So I'm going to put 0 down here. Let's try 2 points. So if I have 2 points, how many ways can I connect 2 points? I'm hoping you can see it's only one way. So with 2 points, I'm going to have 1 way to connect them. You see what we're doing? We're trying to look for some kind of pattern to see if we can predict or guess how many ways we can connect 5 points. Let's try more. So we did 1, we did 2. Let's find 3 collinear points and let's see how many ways we can connect them. So, or how many different connections we can make, right? So we've got 1 connection, 1, 2, 3. Is there any pair that's not connected here? I think we did them all. So we've got 3 ways to connect there. Okay, let's pick up with 4. So we've got 4 points and we're going to see how many different ways we can connect it. And again, we're looking for some kind of pattern. So we've got 1 connection, 2, 3. This guy can connect with this one, 4. This guy can connect with this one, 5. Okay, but then this guy can connect with this one, 6. Uh-oh. Let's see, do I have all the connections there? So it looks like 6 connections. Do you guys see a pattern? Sometimes it's not just looking to see if things are being multiplied, but let's just see how far apart 0 and 1 are. 0 and 1 are 1 apart. 1 to 3 would be 2 apart. 3 to 6 is 3 apart. What number comes after 3? 4, right? So I'm thinking that maybe 4 more. There might be 10 different connections if we have 5. This is my guess. This is my conjecture, just looking at this information. So my conjecture is that if I have 5 dots, it's going to be 10 different connections. Let's test out our conjecture. Let's see if it works out. So I'm going to try again. We've got 1, we've got 1, 2, 3, and 4. Okay, that's 4. And then we've got 5, and then 6, and then 7. This guy is already connected to this one. So then we have 8 and 9. And is there another one? This guy never got connected to this guy, so that's 10. Are there any other connections that weren't made between points? Looks like this guy went to all the ones that he could. This one too. This one went to that one. This one. I think that's it, guys. I think our 10 was true. I think that was good. And I do think that we saw a pattern. And I think that that pattern did make sense and it gave us a true conjecture. Let's look at this next example. Here in example 4, we're going to use the word consecutive. The word consecutive means one coming right after another. So consecutive numbers would be like 1, 2, 3, 4, or 7, 8, 9, or 500, 600, 500, 501. These are consecutive. 500, 501, 502, 503. These are all consecutive numbers coming one after the other. Sometimes we have consecutive, even, and odd, but when you're talking about consecutive numbers, that's what we're doing. One after another, and usually consecutive integers. Let's look at what they're asking us. It says numbers such as 3, 4, and 5 are called consecutive integers. Make and test a conjecture about the sum of any 3 consecutive integers. So let me get this out of the way so we can talk about that. The sum of any 3 consecutive integers. Well, in order to make a conjecture, we've got to look for a pattern. And to look for a pattern, we've got to test some of these things out. So let's go ahead and start off with 3, 4, 5 because that's what they gave us, and we're going to find the sum. Sum means the answer you get when you add things together. So the sum of 3 plus 4 plus 5 is 12. All right, that's fine. Let's try 1, 2, 3 because let's not do the hardest math in the world. 1 plus 2 plus 3 is 6. Let's try 10, 11, 12. When I add those guys up, I end up with 33. I don't know. Anybody seeing anything? So let's go ahead and put a few more out there and let's see if we see something. So I did a couple more and I'm wondering if you see any pattern. Pause me and see if you could see it before I give you an idea of what's going on. All right. So if you're looking at what I'm looking at, I'm seeing a little bit of thing. This is also another place where multiplication skills are important. So I'm looking at the middle number and I'm looking at the answer. The middle number and the answer, the middle number and the answer. Do you see anything right now between the middle number and the answer? Any pattern, any relationship? So your multiplication tables might show you that 4 times 3 is 12, 2 times 3 is 6, 11 times 3 is 33, 6 times 3 is 18, 101 times 3 is 303, 51 times 3 is 153, and 8 times 3 is 24. So my conjecture is when you take the sum of any 3 consecutive integers, the middle integer times 3 will be the sum. So here's our conjecture written out. The sum of three consecutive integers will equal the product. That's the answer you get when you multiply. The product of the middle integer and 3. All right, let's do this last example before you get a few to try on your own. It says a student makes the following conjecture about the sum of two numbers. We're going to find a counterexample to disprove the student's conjecture. So here's the conjecture. It says the sum of two numbers is always greater than the larger number. When I add up two numbers, your answer is always going to be bigger than the larger number. Let's try it out. Let's think about that. So like 1 plus 2, the sum is 3. Well, that doesn't disprove it. That proves it because 3 is bigger than the larger number 2. Can you think of two numbers that I could add up such that when I add them up, the sum is not bigger than the larger number? Negative numbers, maybe? Let's try. -5 plus 7, right? That's going to give me a +2. So the sum of -5 and 7 is +2. Let's check the conjecture. Let's see if we proved it false. The sum of two numbers, that's these two, is always greater than the larger number. Nope. 2 is not larger than 7. So we have disproved this conjecture. I hope it made sense. I know it was a lot. Take your time copying, look at the video again, come ask me questions. Let's make sure it makes sense. But for right now, you got these guys to try. These aren't too hard. You're going to figure out what is the next picture in this pattern. And then here you're going to choose from one of these to figure out what the next picture in this pattern would be. I look forward to talking to you guys soon. Please take care. Bye-bye.